Now that we have chosen a forecasting technique, we need to measure how accurate it is. So we're going to look at forecasting error. And forecasting error is the difference between our actual values and our forecasted values. And we're going to compare the actual values and the forecasted values for a given period of time. So for example, here's our associative model, and we had sales of 46 when there were 9 reported break-ins. And our forecasting model that we created estimated that the number of sales should be 45.61. So we can find our forecasting error by taking our actual, that's our sales, 46, and we can subtract the forecasted of 45.61. Notice when we do that, we get 0.39. If you have a positive forecasting error, it means that your actual was higher than your forecasted. Now let's find the forecasting error for the next set of numbers. So here the actual was 18 and the forecasted was 19.96. So notice our forecasting error is 18 minus 19.96, which gives us a negative 1.96. So when you have a negative forecasting error, your forecast was higher than your actuals. Well, we can find the forecasting error for each of our forecasted numbers. What we really want to know is how well the overall model works. Not just how well we did on one point, but how we did overall. And so we have methods for measuring forecasting accuracy. The first one is called a mean absolute deviation. When we talk about a mean absolute deviation, we're taking the average of the absolute value of our forecast error. So if you look at this formula, you see the sum divided by n. This part simply tells you that it's an average. What we care is, what is it an average of? Well, we can see these straight brackets here, and that's what tells us the absolute value. And we're going to look at the difference between the actual minus the forecasted. So here we're looking at the average of the absolute value of the forecasting error. So let's just take a look at that. So if here's our sales and here's our forecasted sales, then our error was 0.39. When our sales were 18 and the forecasted sales were 19.96, our error was negative 1.96. To find the mean absolute deviation, we would take 0.39 and we would add 1.96. Notice we got rid of the negative. We took the absolute value of the error. And then we would add 0.04, and then we would add 6.51, again getting rid of the negatives. Absolute value gets rid of the negatives of all the numbers. So we would keep going, and we would add up all of the forecasting error. That gives us the top part. And then we would divide by the number of numbers that we have here. So here we have 3, 6, 9 data points. So we would divide by 9. Okay, so at MAD, we take the absolute value of all the errors, and then we simply find the average of them. We add them up, we divide by the number of numbers. A lower number indicates a better forecasting error. With MAD, we're going to weigh the errors equally. Okay, so a 0.39, a 1.96, we're adding those up, we're treating those as the numbers are. Okay, so everything is essentially has an equal weight. When you are using the mean absolute deviation, you need to do a comparison. So you need to be able to compare the mean absolute deviation from, say, an associative model to a naive model. Same data set, and then you can see whether the associative model or the naive forecast is a better method. The lower the MAD, the better method it is. But you have to have something to compare them to. There's a YouTube video where we do these calculations in Excel where you can see more of this. The second way to measure forecasting accuracy is what is called the mean square error. The mean square error is the average, right? There's that sum divided by n of the squared forecast error. So whereas the mean absolute deviation weighted each forecasting error equally, this one is going to emphasize larger errors. So if we have one particular data point where we were really off and the rest we were great, the mean absolute deviation won't really show that. The mean square error, because it's going to square that big error, is going to make it even bigger, and so it's going to have a much bigger impact. So this forecasting accuracy method is when you want every single data point to be as accurate as possible. The mean absolute deviation is when you want the data points on average to be accurate. Okay? This one's mean square error is emphasizing each individual point. In this case, we need to take the forecasting error and square it and then find the average. So if we go to our data set here, so here's our sales, our forecasted and our actual, and we found the forecasting error. To find the mean square error, we're going to take 0.39 and square it, plus our negative 1.96 squared, plus our 0.04 squared, plus our negative 6.51 squared, and so on. And it's an average, so we add it all up, and then we divide it all by the number of numbers, which we had 3, 6, I believe we had 9 numbers there. So we square each error, we add them together, we divide by the number. With the mean square error, you're going to need to compare different forecasting methods. So again, associative model could be compared to the naive approach. The smaller mean square error is the better model. The third method for forecasting accuracy is called the mean absolute percent error. So it's going to take the average absolute percent forecast error. All right, let's break it down. Here's the average in the formula. So we're going to take the average just like all the other ones. The difference here is we're going to take our error and we're going to turn our error into a percentage of the actual number. And since it's a percentage, we're going to multiply it times 100, so we're dealing with whole numbers instead of fractions. The benefit of the mean absolute percent error is that it's going to emphasize errors that are a large percentage of the actual. So it's comparative. And the benefit of this is that if you are looking at data that, let's say you're looking at stock prices, and one stock is $2, $3, $5 stock price. Another stock is $1,000, 98 or 989, 890. Those prices are all in the hundreds. Your first stock was all in the single digits. So with those two stock prices, we could fit models to them, but with the mean absolute deviation and the mean squared error, we can't really compare the two stocks and how well the models fit for the two. We would have to compare two forecasting methods with the same stock. But mean absolute percent error puts it into context of the relative value of what you are forecasting. And what it allows us to do then is it allows us to start to compare how well models fit on different data sets. So when you find the MAPE, if you take 100 minus the MAPE, it's telling you the percent accuracy. And you're looking for an accuracy over 70%. So for example, if you find that the MAPE is 11.5, then you can take 100 minus 11.5, and you get the fact that that model is 88.5% accurate. If you get an MAPE of 34.1, you can take 100 minus that, and you get that that model is 65.9% accurate. So the benefit of the MAPE method is you don't actually have to compare one model to another for a data set. You can get an idea of its accuracy on its own. It also allows you to now do a comparison. If you're forecasting different data sets, you can now look at the accuracy of different sets of data. So how do you calculate MAPE? Well, we need to find our forecasting error divided by the actual. So we would take our forecasting error of 0.39 and divide it by the actual of 46. We would multiply that times 100. Okay, so 0.39 divided by 46 times 100 is 0.85. And then we do the same thing with the next one, negative 1.96. Now notice it's an absolute value, so the negative goes away. And we're dividing it by the actual value of 18 and multiplying it times 100. So 1.96 divided by 18 times 100 is 10.89. We would do this for every one of our forecasting errors, and then we would add these together, 0.85 plus 10.89 plus all the other numbers, and we would divide by the number of numbers. We divide by 9. To see how to do this in Excel, please see the other YouTube video. Now, when we are looking at how accurate our forecast is, we can create what is called a control chart. So what we're looking at is we're looking at the errors, and are those errors what we think they should be? Well, on average, your errors should be 0. If you have a line of best fit that's in between your data points, then sometimes your actual data is going to be over, and sometimes your actual is going to be under. On average, it should be 0. If this was our forecast, see this line down here, and all the actuals are up here, then we know this is a terrible forecast because the average error is not 0. Because every single one of our actual points is above the forecast. Your forecast should be essentially half the time above and half the time below so that your average error is 0. Okay. Now, we can actually plot what is called a control chart to show what's happening with those forecasted errors. So we said that on average, our forecasting error should be 0. We also want to look at, is the forecasting errors ever way too much in the positive direction or the negative direction? So we need an upper bound and a lower bound for our control chart. To find your upper and lower bound, you're going to find the standard deviation of the forecast error. So if you find the mean square error, you would just take the square root of this number. And remember that mean squared error takes your errors squared and finds the average of them. So if we find the mean squared error, we take the square root, which for our break-in example is 3.61, then our upper control limit is 2 times that 3.61, or 7.28. The lower bound is a negative version of that, so negative 2 times 3.61, which gives you negative 7.28. You can then plot your forecasting errors to see where they live in that control chart. Are they all above 0? If our forecasting errors are all above 0, we know it's a terrible fit, like the graph that we can see here. All the forecasting errors, all the actuals are more than the forecasting. So all of our dots in that case would be up here above the 0 line. If our forecast was up here and the actuals were all down here, then on our control chart, the dots, the errors, would all appear below the 0 line. What we're looking for on our control chart is that there's no patterns. If we see a pattern in that forecasting error, then there was some seasonality that we didn't account for in our model. We never took out the seasonality, so no patterns. The other thing we want to do is we want to make sure that the average error is 0. Okay, so we should have some above and some below. So we're looking for something like that. We want to make sure that none of the errors are outside of those upper or lower bounds. So that would be some irregular variations we hadn't accounted for. We want to make sure that there's no pattern in the data and that it's on both sides of our 0. So this would tell us whether or not we had a good forecasting model.